Hi, this is Giovanni da Prat, the author of the content of this presentation, and also I'm going to be your speaker. In case you have any doubts, please do not hesitate to contact me via email or either WhatsApp. Okay, I do have other presentation already published. It's a basic examples on pressure transient analysis in the case of a homogeneous reservoir. And I have been requested to do something similar, but in the case of a naturally fractured reservoir. So what we're going to see is a brief presentation on how the analysis is made in the case that we deal with a fractured reservoir, and also using the two porosity model. Okay, let's start with the objective of the test, so you're going to have an idea how the method is going to work, the interpretation process, I mean. So we need to determine the naturally fractured reservoir parameters, omega and lambda, according to the two porosity model. There are other models for naturally fractured reservoirs, even three porosity, but in this case we're going to use this one here. In addition to that, you need to determine the reservoir pressure trend and the limit nature. And we're going to apply both a single event analysis, let's say the classical well test analysis, where you get an event, a build-up or drawdown, and then you try to derive the reservoir parameters, and then you do the simulation of the whole test. And the convolution method, which nowadays is quite common to use, and we're going to see the advantage in using the convolution method. So here there are the reservoir and well data. Here we know it is a naturally fractured reservoir. In many cases, you just have to find out what type of reservoir we're dealing with from the interpretation, but here it is quite clear from geology and petrophysics that we're dealing with a naturally fractured reservoir. Initial pressure, saturation pressure, thickness, you can see you have all these values here. We're not going to detail all of them. We're dealing with an oil, a GOR of 561, and other relevant fluid parameters. Some of these, like the formation volume factor, we gather from program correlations, not PBT, but they're very close, probably 5% difference. Before we enter in the mathematical details of the interpretation, let's just have a look at what a naturally fractured reservoir is. You can see here that these are cores taken from a well in the Maracaibo Lake, Venezuela. And it is not the only, there are many fractured reservoirs over the world. Iran, for instance, it has quite a potential fractured reservoirs, gas. The States also. But the idea is a system, like you see here, where you have fractures, like the one you see here, and matrix. In many cases, the matrix is also made of microfractures. There are cases where a fractured reservoir like Huamampampa in Bolivia is a formation that actually the matrix is not the classical one porosity, it's made up of many microfractures and acts like a matrix for the other fracture that you see here. You can see here that the oil, in this case, is from the fracture. Still you can see here oil. And the situation with these systems here is, where is the reserves located? In the fractures only, and also the matrix has reserves. And actually, if that's the case, then the reserves are contained in the matrix, and the fractures just act like a bridge to the well to get the oil. So the mathematics of the modeling is like having two diffusivity equations for considering two homogeneous reservoirs. The fissures or fractures are, the fracture system is an homogeneous reservoir, and the matrix system, or the matrix has an homogeneous reservoir. And they're tied by the relation which is telling us the feeding from the matrix to the fractures. So if you solve that equation, as I said, over 15 years ago already was solved, you're going to end up with the model that you expect to simulate the data when you get data from a fracture reservoir. So here is a little bit what we can see the dynamics. Let's say the well is shut in, you open the well, there is a drawdown here, there is a pressure here, and this is matrix is its initial pressure. Once you establish well flowing pressure here, then major contribution is the fractures that you see here, and then eventually there is a drop in pressure here, and depending on the matrix permeability, this is going to start the process of feeding the fractures. So the way to feed the fractures could be like a pseudo-steady state type, which is you got one pressure here in the fractures, one pressure in the matrix. It's just a relationship like, let's say, Darcy's law is the difference with some constants related to the matrix block size and other parameters. In the case of transient pressure profile is another model. So when we reach the two porosity model, you have a choice of choosing either the pseudo-steady state pressure profile or the transient pressure profile. In this case, as the name says, this is a transient, and then the feeding is going to be depending on time. And these two parameters here, lambda and omega, they're related to lambda especially is related to the matrix permeability of this ratio here. The lower the matrix permeability, the lower the lambda is. And then so there are some shape factors that, as I said, are related to the dimension of the blocks. There are many publications here, and I can refer to them if you're interested. And then there is another parameter related to the storativity capacity. This is omega, which relates the hydrocarbon contained in the fractures over the total hydrocarbon content. So let's say that omega is equal to 0.1, then it means that 10% of the hydrocarbons are in the fractures. Okay, as I said before, there is these two diffusivity equations in parallel, and then they be linked by the feeding of the matrix to the fractures. When you do that, and then you're going to have, this is your expected solution in a dimensionless time, a dimensionless solution. It means that after we have well storage, which is always present no matter what, even information testers volume, you do have a well storage. After you get out of the influence of the well storage, you're supposed to have here some radial flow, infinite radial flow associated to the fracture system. And then there is a transition. The shape, the trend of this transition, it depends on if it is a double porosity pseudo-steady state transition or transient. In which case, in this case here, you can have, the valley could be deeper, and in this one here, the transient is going to be different from here, but at the very end, they should be, as you may expect, the same when you get the infinite acting radial flow for the total system. So this has been already in place. Software is prepared to type of algorithms, then okay, you can train your system with this type of signature here. I took this information, which is very simple, from the Kappa Engineering DDA book. So let's go to our test. And test is, even though it's inspired on field cases, I have to redesign it just to avoid confidential type of things. But just to tell you that it is inspired on what you see in many cases in the field. It's a trend here. There are some build-ups like monitoring. Actually, you have a production period here, which is several drawdowns here, and then previous to that, there is a cleaning part. Then you do a drawdown, 300 hours, 200 hours, and 600 hours drawdown, and finally a build-up. You can see the build-ups, probably the one that are acquired in the field. In many cases, you don't acquire these, and you just acquire a few points during the last part of the drawdown to have a reference for your delta P's, and then you do your build-up. And in many cases, you only count with the build-ups, okay? Even though you can have this bottom hole pressure from extrapolation from the wellhead pressure and rates. So what I'm trying to say that this, if it's not directly measured, you can get it indirectly by using gradients or correlations. Okay, so this is your rates. And here, as you see here, we're going to have 4 build-ups. And the idea I'm going to show you here is to do the analysis and also to see the deconvolution benefits. In cases like this, where you can imagine just looking this, no need to do any analysis, but the build-ups are short, as you can see here. And this, as I said before, so we're going to start, maybe if you got a lot of experience, you already start with the convolution, because basically there is one single phase flow. Reservoir pressure is always above the bubble point. You got one phase, and that means it's a requirement for to apply the deconvolution also. So let's do first the single event analysis, or the classical analysis. I call it single event because it's just one build-up, or in this case, or drawdown. I analyze, and then I try to simulate the whole test history, the classical way. So here we're going to have the 4 in one plot. You see here all the 4 build-ups. Some of them are, you don't see here, but there are 4. And this also you can do in one plot to have all these three drawdown periods, which are different in duration, as we showed you before. This one is 300, or let's see, don't remember where, it's 300, 200, and 600. Okay, so what let's go like step by step, like not knowing, basically probably you starting with this business of analyzing data. What you do is the first thing is to try to identify flow regimes, okay? Like here, we're going to use the first build-up. We have used other build-ups. We're going to use the first. And then you can see here wellbore storage, then keep wellbore storage decreasing. Then finally here, you're supposed to have a stabilized or a flat part as this tool. By the way, this tool here is a flow regime diagnostic tool. Is included in the program Sapphire if you use that software. So the last point during the build-ups is here. And let's go back again just to make sure what are we expecting? We're saying that if it is a two-porosity pseudo-steady state, so the behavior should look like this one here. The signature is like this one. So it seems that we're okay here. It's going down. Actually, if the test stops here, you may consider other models, not two-porosity reservoir. But here we're, as I said, from geology, petrophysics, and other information, we're dealing with a naturally fractured reservoir. Situation is also like this. It could be a naturally fractured reservoir, but the matrix has no reserves, no permeability, in which case we're going to see something like homogeneous reservoir. That's very important to know, because in many cases they tell you it's a fractured reservoir, but actually fluid is only in the fractures. There is no matrix contribution. Therefore, you don't see this valley here, and you're going to see just a plain radial flow, a straight horizontal line. Okay, so according to this tool here, it says that we're expecting to see the infinite acting radial flow for the total system at about 700, 800 hours. Probably you won't decide, maybe your test is like this one here in real practice. You don't stop production, or maybe you can ask for a 20 hours or 30 hours. So if you go further than this, you need to be aware that it may take, like this case here, over 600 hours just to get the total system radial flow. So from now you have to say, okay, how about if I have only this build-up? Okay, I will try to analyze it using a two-porosity model, and maybe you're going to have so much to here. And from there on, you don't know. I mean, you can assume and try to do the analysis with that, as we will see. But if there are discontinuities from here on, this is not necessarily the trend, okay? From here, even from here, if you got discontinuities like faults or barriers or changing mobilities, they're going to affect, the effect is going to be superimposed over like here, you see. Here, I don't see radial flow here because still there is a wellbore storage effect. So even though it's minimized, but in any case it masks, you don't see a horizontal line here because it is there if you take out the wellbore storage contribution. So let's go to the fourth drawdown. In this case, the drawdown was enough to reach, let's say, total system, but we don't see here, as expected according to this tool, that this is stabilized. And actually from here on, the trend, the pressure trend that you can see, one of the benefits of the derivative that you can see here, it departs. It means that there are discontinuities that are getting superimposed to what you expect here, and the resultant is this trend here. This is the drawdown 4, and we're going to have a look now for the drawdown 6, which is the longest drawdown, I guess, it's 600 hours. And you can see here that, again, there is no any flattening here from the actual derivative. Rather, it keeps tendency going up, and it looks like we're reaching pseudo-steady state because the slope is around 1 from this point on. And that means that it's a closed system, And if you start playing with this regression by experience, you're going to use some boundaries, some closed outer boundary, and start feeding the data. So what we did here, this is the reason these are tools too. Once you use these tools, they already make a previous calculation. So when you go and simulate, you can use these values, these local values, that will help you the modeling. I will show you later when we do the example. Later on, we'll use Sapphire, and then I reproduce these features here. Okay, now let's say that we got a simulation for this drawdown. You can see here is quite nice over here. And at the end, actually, there are still, if test continues, you're going to see that the most probable trend is this one here, which is 1, the slope of 1, which means pseudo-steady state behavior. This is a semi-log, and now a proof when you do the one single event analysis or classical analysis, you requested to do the simulation of the whole test as a validation. What you see here, that we did using the values of the results from this drawdown here, we have been able to simulate the whole test history, as you can see here. And not only that, also you can, because it's a closed system, you can calculate the reservoir pressure. So you have your bottom hole pressure, reservoir pressure, and then this is the trend that is shown here. Okay, as a result now, we got omega, what the result we were looking for. The storativity ratio used to be called. It means that 4.7% of the total hydrocarbon is contained in the fractures. Then you have a lambda value, which is e to the minus 7, which is not small. Well, you can say minus 7 is small, minus 6 is small. But in this range of lambda values, it's not as small. It's not small. So we can see the transition, the feeding. If you don't see a feeding, what I'm calling the feeding is, this is when the feeding starts, matrix feeding the fracture. At what point in time this is happening, could be either here or could be here. It depends on lambda values. And this is okay, minus 6 is okay. If you got minus 4, then you're going to have that this value here is beginning over here, because it's related to the matrix permeability, directly related to the matrix permeability. Okay, we got these distances. 1130 for the south. Well, southeast, northwest, it's not. It's just a reference. The way it is, you can, rotate your rectangle according to, if you want to position according to your map. But it's actually in the middle of a rectangle. One side is twice, or a little more than twice the other sides. But eventually 3 sides are not equal, but not very far apart. So you got your stock tank initially in place, and because you got this area here, and you're talking about an area of 2 to 7 acres. Your final pressure is 4494.06. That's the pressure at the end of the test, which is this one here. So interpretation of pressure transient data acquired during the longest drawdown events allow to identify not only a two-porosity type of reservoir, but also a closed rectangle type of limit, based on presented flow regimes. Okay. In the case of build-ups, the periods were not enough to reach infinite acting radial flow regime for the total system. And actually here we're introducing that this could be a good example for the deconvolution method to apply. We're going to do next. Okay, probably you're familiar or not with the deconvolution method. If you're not, I already have other, you tell me and then I'll send you some basic information. But you have to be nowadays aware that this is a method that many people is very common to use. So we're going to compute this deconvolution. We're going to fit with these 4 build-ups that you see here, you have seen before. And then you enter, you're going to see when I use the software, how we get this, this resulting, let's call it deconvolve function. It is representing 1200 hours testing time, a constant rate type of solution. So you see here that just using the build-ups, you can see that there is this two-porosity feature here, because during the build-ups is shown, and the deconvolve, and you know the last, we were about 1200, I guess 1000 total testing time. Now you got 1200, which you add more time as the convolution, it says inherent in the convolution. You got your testing time is the total testing time, including build-ups and drawdowns. So if we do the simulation of using the deconvolve pressure, now we're not simulating one drawdown. Well, actually it is a drawdown at a constant rate, but not to get confused with the longest drawdown that we did in the single event analysis, which lasts 600 hours. This is now 1200 hours. Still, you can see here that this is the way to go to the steady state. It could be better defined that in the case of the last the drawdown event, but it could have been a good idea just to have more points, so to get the trend more defined. But anyway, this is inherently in any interpretation process. Here there is not quite a good match. I tried so many, I tried to do it many times, I could not get it. Probably if you get it, you tell me, I send you the data, you try to get it. It will be a pleasure to discuss with you. But the other, you see this is going to affect omega in a way, and also affecting all parameters. It is a nonlinear regression, but I don't use any parameters constant. I used to go with all the parameters and to get a final solution. Okay, and this is for the semi-log for the build-ups. You can see here that also there are no, this is a good match here, but here it's not as we like to, or even for this build-up here, this is the convolution solution to the analysis of the deconvolved pressure is not reproducing this build-up, which is not happening in the previous case in the single event type of analysis. Okay, these are the results. And again, omega is 0.042 compared to previous result for the single event analysis that it's about 0.047. This is, we're having 0.042. This is in the order 2 e to the minus 7. A little bit difference here is this side here is quite, not twice, but let's check again. Here we're having 2200, and over here we're talking about 3800. So it means that the area of drainage is bigger, and therefore, being bigger, for that amount of oil, cumulative oil, your pressure, average pressure at the end of the test is going to be bigger than the one used that we got with the single event analysis. Mainly because you can see here, to get the match, we use results, which means we needed to use a bigger area. Okay, we'll do like in the past, in the single event, we have to reproduce the whole test history, as we can see here. It's okay. And the major difference is going to be here. So question is, which one is right? That could be one you may ask. So surprisingly, I would say both are right. Maybe there is no way to say that one is better than the other, or one is the one to be considered. So this is, you see the difference, start splitting. Initially, probably you don't see, because the pressure is not going in any way, is not going down as fast as we start depleting. So conclusions from a practical point of view: the right results for reservoir parameters, as we saw, skin factor, limit nature, are the same using both methods. And regarding drainage area, there is a difference of 3, as we saw, 3 to 1.5 for using the deconvolved pressure, and 2 to 7, which means that the trend of the reservoir pressure is different. So if we compare results, even though there is quite a good pressure match obtained using both methods, we have to say that the single event analysis is of better resolution. However, pseudo-steady state flow regime is not well defined in neither of the two methods. Certainly, we got a point, at least the last point is in the trend, but it could be a good idea to have it more points. Reason maybe the build-ups were short, so even though we had almost 600 hours extra for the deconvolution, we still at the early stage of the pseudo-steady state. So it means that both are an interpretation, and therefore both should be valid, because it's an interpretation and is based on playing with drainage. By the way, we should say this, quite a benefit. None of the build-up events have the duration as to identify infinite active radial flow in the total system. So what we're going to do now is we're going to use the software, and then we start with the build-ups rather than the drawdowns. We start using the deconvolution first. Okay. Another very important to know, the deconvolved pressure is not a measured pressure. Okay? It's resulting from a transformation process. We're transforming rates to one single rate. It's a process, but the resulting deconvolved pressure is just resulting from a process. It's not a direct measurement. So based on things like on these comments here, I have to say that both methods are equally valid. But again, any comments, please don't hesitate to contact me.